Quick, how does nuclear energy work? Did you say steam? Because it's steam. Hello and welcome to the Chemist's Codex. My name is Peter and I like to talk about whatever happens to catch my interest. And today we're talking about one of my favorite things, nuclear power. Because I feel like there are a lot of misconceptions about nuclear energy. There might be fewer misconceptions nowadays, but for the most part I think nuclear energy still has a bad reputation. At its heart, any power plant with a big spinning turbine is basically just a giant kettle. It's a concept that would be perfectly understandable to a Victorian engineer. Coal, natural gas, and nuclear all operate on the same principle. You generate an incredible amount of heat, use that heat to boil water into steam, and then blast that steam at a giant turbine. The turbine spins a generator, and boom, you got electricity. It's surprisingly old school technology. The real difference is what you use to generate that massive amount of heat. For most of human history, making heat meant burning things. Wood, coal, oil, gas, it's all just combustion of hydrocarbons. It's messy, and it releases all the carbon that whatever you're burning has stored away. But a nuclear power plant doesn't burn anything. Instead of using the energy stored in chemical bonds, it taps into the colossal power holding the nucleus of an atom together. Atoms are mostly empty space. There's a fuzzy cloud of electrons whizzing around a dense nugget of matter in the middle, which we call the nucleus. For most elements, that nucleus is nice and stable. But for some really big chunky elements, like uranium, the nucleus is too big for its own good. It's like a Jenga tower that's on the verge of collapse. For nuclear power, we tend to focus on one particular isotope of uranium, uranium-235. It makes up less than 1% of all the uranium we dig out of the ground, but it's also fissile, meaning it can sustain a nuclear chain reaction. If you can hit a U-235 nucleus with a stray neutron traveling at the right speed, the nucleus will eagerly absorb the neutron and split apart. This is nuclear fission. When that nucleus splits, it breaks into two smaller atoms, which fly apart as a large amount of energy is released. This blast of energy appears because a tiny bit of the atom's mass gets converted directly into energy. But this fission reaction also releases more neutrons, and this is the secret sauce, the key to a sustained nuclear reaction. Those new neutrons can fly off and smash into other nearby U-235 atoms, which causes them to split. Each of those split atoms then releases more heat and even more neutrons, which split more atoms, which then split more atoms, and so on. It's a chain reaction. It's kind of like dominoes. Each one that falls knocks over the next. In a bomb, this chain reaction is allowed to run wild, and an uncontrolled cascade of nuclear fission creates a massive explosion. Inside a nuclear reactor, the entire goal is to tame that cascade. To do this, two key tools are used. The first are control rods, often made of a material that's good at absorbing excess neutrons. They act like sponges for the neutrons, sucking up enough of them to keep the chain reaction under control. The second tool is a moderator, often just plain old water. The neutrons released by fission are moving too fast to be easily absorbed by other U-235 atoms. The moderator's job is to slow them down, turning them from fast neutrons into thermal neutrons, which are much more likely to cause another fission event. By carefully raising and lowering the control rods, operators can fine-tune the system so that for every atom that splits, one of the neutrons goes on to cause another atom to split. This creates a stable, sustained, and immense source of heat without burning a single bit of fossil fuels. Okay, so we've got a stable chain reaction blazing away, generating a godlike amount of heat. But how do we use that heat to boil water and spin a turbine? This is where the most common reactor design, the pressurized water reactor, or PWR, comes in. It starts in the reactor core, where you have fuel assemblies packed together, each one filled with little pellets of uranium fuel. This is where the fission is happening and where it gets incredibly hot. To move that intense heat, a PWR uses a primary loop, a sealed circuit of pipes filled with water that is constantly being pumped through the reactor core, where it flows over the fuel assemblies and soaks up all that fission heat. Now you might be thinking, wouldn't the water just turn into steam? And you'd be absolutely right, but the trick is where the pressurized part of the name comes in. The water in this loop is kept under crushing pressure, which keeps it from vaporizing. At these extreme pressures, the water is physically incapable of boiling. And that's actually really important, because this water is flowing around the fuel assemblies, so it becomes radioactive. And we don't want radioactive water escaping into the atmosphere. So from here, this super hot pressurized water gets pumped from the reactor into a steam generator. The radioactive water from the reactor moves through a completely separate vessel of water in a series of tubes. This is the secondary loop. The water in this loop is at a much lower pressure. When this cooler water touches the scorching outer surface of those tubes, it vaporizes into steam. This design is a critical, fundamental safety feature. The radioactive water in the primary loop never mixes with the water in the secondary loop. The heat gets transferred, but the radioactivity stays safely contained within the primary loop. Let me emphasize that again. The water never mixes between the two loops, and the radioactivity is entirely contained. From here on, it's a standard power plant. The resulting steam is piped over to a turbine where it's blasted against the turbine's blades, spinning the turbine shaft. That turbine is connected to a magnet that spins inside a coil of wire, which pushes electrons down the power lines and into our homes. And then to complete the cycle, the steam is pumped through a condenser to turn it back into liquid water. This is often achieved through yet another loop of water, or those giant cooling towers you see. Those towers are basically just radiators for the whole system, releasing harmless water vapor into the atmosphere. So those large clouds you see coming from the cooling towers, that's not some sort of radioactive smoke, it's just normal steam. While the PWR is the most common reactor design, there's another major design that makes up a significant part of the world's nuclear reactor fleet: the boiling water reactor, or BWR. It's a bit of a simpler version of the PWR. A BWR simplifies the process by having just one water loop. Water is pumped into the reactor core, and the heat from fission is allowed to boil it directly into steam inside the reactor vessel. That steam is then piped straight from the reactor to the turbine. The upside is a simpler design. There's no need for huge steam generators, and the reactor operates at a lower pressure. The downside? The steam spinning the turbine comes directly from the radioactive core. This means the steam itself is slightly radioactive, which requires the entire turbine and its associated components to be shielded and contained. Both PWRs and BWRs are classified as light water reactors because they use normal or light water as a coolant and moderator. For most of the time we've been using nuclear power, these two designs have been the backbone of the industry. But the fuel that runs these atomic furnaces is just as important. Since most reactors use uranium as a fuel source, it all starts with uranium ore. The problem is most of that ore is going to be uranium-238. This isotope of uranium can be split, but only by very high energy neutrons, so it can't sustain a chain reaction. To get a light water reactor going, you have to enrich the uranium, boosting the U-235 content to between 3 and 5%. This is an entire process in and of itself and not really worth getting into right now. Once the uranium is enriched, it's converted into the stable ceramic powder uranium dioxide, which then gets pressed into a uniform pellet a couple centimeters big. The pellets are baked at a high temperature until they harden, a process called sintering, and then stacked into long tubes to create a fuel rod. Now here's the part that is truly incredible. A single one of those little pellets, small enough to hold between your fingers, contains as much potential energy as a ton of coal, 120 gallons of oil, or 17,000 cubic feet of natural gas. The energy density is on a completely different level compared to fossil fuels. But uranium isn't the only possible fuel for a nuclear reactor. There's also thorium. Now, thorium itself isn't really fissile, it's what we refer to as fertile. This means that thorium will produce fissile material when hit with neutrons rather than undergoing fission. Specifically, thorium will produce uranium-233, and U-233 is fissile and an excellent nuclear fuel. So a thorium reactor is said to breed its own fuel. Thorium offers some major advantages. Not only is thorium more abundant than uranium, but the thorium fuel cycle produces significantly less long-lived radioactive waste. The waste it does create is less hazardous and becomes safe much, much faster. For a long time, thorium was the road not taken, largely because the nuclear industry's early development was tied to the Cold War and the need to produce plutonium for weapons, which is something the uranium fuel cycle does, but the thorium cycle doesn't do all that well. But with newer reactor designs coming into play, thorium fuel is looking like the better option. Today's reactors are still impressive feats of engineering, but most of the currently operating nuclear reactors were built during the 70s and 80s. They're pretty outdated when it comes to reactor designs. But there have been many new reactor types proposed since then. One of the more exciting designs is for the molten salt reactor, or MSR. The first reactors of this type were actually pioneered in the mid-20th century at Oak Ridge National Lab, but were largely set aside until renewed interest sparked in the 21st century. Instead of using water to cool the reactors, MSRs use a liquid fluoride or chloride salt. The salt is solid at room temperature, but is kept at high enough temperatures for it to be a liquid while the reactor is operating. And oftentimes, the fuel will be dissolved directly into this molten salt. This single change brings some massive benefits. First, MSRs operate at, or at least near, normal atmospheric pressure. You don't need to keep the coolant under pressure to keep it from boiling. This eliminates the need for pressure vessels and stops pressure buildup due to gaseous fission products. Many MSR designs also include something called a freeze plug at the bottom of the reactor. It's a chunk of frozen salt that's kept solid. If the reactor ever loses power or begins to overheat, the cooler shuts off, the plug melts, and the entire liquid fuel salt mixture drains into a separate containment tank where the liquid solidifies and the reaction stops. This prevents a nuclear meltdown scenario since the reactor is designed so there will never be an uncontrolled chain reaction. Secondly, MSRs run way hotter than traditional light water reactors, around 700 degrees Celsius compared to the 300 degrees of a PWR. Basic physics, specifically the laws of thermodynamics, says that the hotter your heat source, the more efficiently you can run the cycle. So MSRs are also more efficient at producing electricity. Then MSRs are perfect for something like a thorium fuel cycle. Like I said earlier, the fuel is commonly dissolved right into the liquid salt coolant itself. This means you can refuel the reactor by adding new fuel while the reactor is still running, and you can also remove fission products as they are created. They can even be designed as waste burners to consume the long-lived waste products from today's conventional reactors, turning that liability into clean energy. And the waste MSRs do produce is significantly less radioactive, only needing a few hundred years to be safe. But let's talk more about nuclear waste altogether. For a lot of people, this is the deal breaker when it comes to nuclear power. There's this terrifying image people have in their minds of glowing green sludge leaking from yellow barrels. But the scientific and engineering reality is actually way more manageable and less frightening than most people realize. First, let's be clear about what the waste actually is. About 97% of all nuclear waste is classified as low-level or intermediate-level waste. This is stuff that isn't directly radioactive, but has been in contact with radioactive material. Things like contaminated tools, protective clothing, and industrial materials. It's bulky, but its radioactivity is mild and fades to background levels within a few hundred years at most. This material is routinely handled, secured, and buried in near-surface disposal sites. The real conversation is about the high-level waste. This is the used fuel itself, those ceramic pellets after they've spent several years inside a reactor. It's incredibly radioactive, yes, but there's really not that much of it. All the used high-level fuel in the United States could fit on a single football field and would only be about 3 meters tall. There really isn't that much high-level waste. But what do we do with it, I hear you asking? Some people would have you believe that we don't really know. The truth is that we've had an international consensus for a while now: deep geological disposal. The plan, which countries like Finland have already started enacting, is to seal the waste in incredibly robust casks made from layers of concrete and steel and bury them deep, deep underground. The problem with nuclear waste has never been with the science or engineering behind it. It's pretty much always been the challenge of getting public and government acceptance to build a repository. And the idea that nuclear waste is dangerous for such a long time, it might as well be dangerous forever, that's also a myth. Radioactivity decays, and it decays exponentially. Yes, spent fuel is incredibly hazardous when it first leaves the reactor, but after only 40 years, that radioactivity has fallen to 1,000th of that level. Plus, most nuclear waste isn't actually waste. Somewhere around 90% of the waste is still usable fuel, and through reprocessing we can recover that fuel to be used later, significantly reducing the volume of nuclear waste. However, the United States currently does not reprocess spent nuclear fuel. So what is nuclear energy? Hopefully, after all that, you have a better understanding of what nuclear energy actually is. At its most basic, it's a breathtakingly powerful way to boil water. But it's also so much more than that. It's a technology that taps into the fundamental forces of nature to give us a clean, dense, and reliable source of power. We've seen how reactors use a tamed nuclear reaction to produce steam to turn a turbine. We've peered over the horizon at a new generation of reactors that can produce energy more cleanly and more safely than before. And we've tackled some of the tough questions regarding nuclear waste. Nuclear power isn't a magic wand. No energy source is without its trade-offs and challenges. But in a world that is desperately struggling to power itself without blanketing the planet in carbon, nuclear power remains one of the most powerful and proven tools we have. It's a technology born from the deepest understanding of matter, and I hope its story is far, far from over. Thanks for watching. Nuclear power is something I've been fascinated by ever since I was a teenager, and the more I learn about how nuclear power actually works and new reactor designs, the more baffling I find it that people are against it. Sure, there have been instances like 3 Mile Island, Chernobyl, and Fukushima, but can you name any other nuclear disasters besides those? And even with those, disasters only happen because people were doing things they shouldn't have been doing in the first place. But I want to hear from you. What are your thoughts on nuclear power? Are you in favor of it, or has this video swayed your opinion at all? Let me know down in the comments. And if you want more videos about the science at play in our lives, make sure to subscribe so you don't miss my next video.